In the last video, we made a blank canvas from an existing picture and also learned how to mathematically model physical nails and strings on it. In this video, we shall take what we have learned and see how we can draw strings between any two nails and consequently between all possible nail combinations, and finally, how to store them for future use. So let's go ahead and draw a string on a blank canvas. For this example, I'll assume we are going to be using 50 nails. The nails are numbered starting at 0 all the way till 49, and we will be drawing the string from, let's say, nail 7 to nail 25. To do that, I'll make a copy of the program that we wrote in the last video to generate a blank canvas and add some more code that draws a string on it. This is the part which generates the blank canvas by making all pixels white. We will add some more lines of code after this part to generate the thread on the canvas. As a first step, let us derive an equation for a thread that is wound between two nails. In the last video, we saw that if we have n nails on the canvas, the angle between any two consecutive nails is 2 pi over n. Therefore, theta is 0 for nail 0, theta is 2 pi over n for nail 1, 4 pi over n for nail 2, and so on. And for the mth nail, where m is less than n, theta would be 2 pi times m over n. Using these facts, the coordinates of any nail at a general position m is given by xm, ym is equal to r plus r cos theta m, r plus r sin theta m, where theta m is 2 pi times m over n. Now that we have the coordinates of any nail on the canvas, let us consider two general nails m1 and m2 that are not the same nail, that is m1 is not equal to m2, and also m1 and m2 are less than n. Using the slope-intercept form of a straight line, we get the equation of any straight line between m1 and m2, and presumably the model for the thread strung between nails m1 and m2 as shown on the screen. I encourage you to plug these values into the relevant equations and verify the correctness of what you are looking at. It's a pretty straightforward process. I said I'll be using nail 7 and 25 a while ago. So let's go ahead and see what the coordinates are for those and the equation of the line between them. The coordinates for these nails are what you see on the screen, with theta for the nails being 2 pi times 7 over 50 and 2 pi times 25 over 50. But we have a problem. We don't know what r is. As we found in the last video, r is half the width of the canvas, but we don't know that either. So what do we do? Remember, a digital computer image is made of pixels, and any image is a certain number of pixels wide and a certain number of pixels high. So I am going to make a decision and say that the width of the image is equal to how many pixels wide the image is. This choice may seem arbitrary, and in a sense it is, but I think it is going to turn out well. This basically assumes that a pixel is one unit of length wide and high without any regard to the unit itself. The unit may be millimeters, it may be centimeters, or even kilometers for all we know, but we will worry about that at a later stage. For now, we will just say a pixel is one unit of length wide and high and go from there. The image I am using for this example is 400 pixels wide and 400 pixels high. Therefore, the radius r becomes 200. We don't have to calculate these coordinates because we don't want them. What we actually want is the equation of the line that goes between these nails, and therefore we are going to use these numbers in the line's slope-intercept equation. Doing all that, we get the equation of the line as you can see on the screen. The ideal model of the line exists only in the mathematical world of abstraction, where space is continuous and smooth. But a digital computer image is made of pixels, and therefore a pixel is the smallest unit of manipulation in it. What this means to us is that an image will not be smooth and continuous like its mathematical counterpart, and therefore we somehow have to translate a line into a set of pixels on the canvas that we are gonna set some color to. So let's see how that works by taking an example empty canvas that is 6 by 6 pixels on which our ideal line is superimposed for reference. To draw the line on the canvas, we shall follow a simple rule. Any pixel over which the line passes shall be shaded black. That is it. We shall begin doing that by numbering the x and y axis to align with the pixel grid. Since each pixel is one unit of length in both width and height, if we start at the origin with the first column of pixels numbered 0, each column of pixels after that would be numbered 1 greater than the previous column, and likewise for the y-axis. By doing that, any pixel on the grid could be identified with two numbers, the row and the column in which the pixel resides. This works out just like how we would define a point using two numbers. The difference between an ideal blank canvas and its digital image counterpart is that in the ideal one, I can move along the canvas in a continuous fashion. But in the digital canvas, I can only move in multiples of pixels. This introduces a degree of graininess into the digital canvas which cannot be avoided. Now that we know this, let us go ahead and take the model of the line and draw it onto the digital canvas. Imagine a line that passes over our 6 by 6 pixel canvas whose equation is y equals mx plus c. We shall take the line and break it into 6 segments, each of which falls inside one of the 6 columns of pixels. By doing so, we can take one unit of length along the x-axis at a time and using that, determine what unit of y-axis that segment of line belongs to. When we do this for all units of length along the x-axis, we would have a set of pixels with us, which represents the line on the canvas. Let us take a unit of length on the x-axis that lies between xk and xk plus 1. Here a variable x could be anything between those two limits. And now we shall rewrite the equation of the line in terms of x instead of y. By doing so, we can substitute this equation's right-hand side, which contains y, into the previous inequality, yielding a new inequality giving us the range of the y coordinate of the line. But as you can see, y could end up between fractional limits which do not align with the boundaries of pixel rows on the y-axis. Therefore, we shall round down the lower limit and round up the upper limit, which puts the values of those limits to align with those boundaries. With this, we have all the math necessary to write our program except for one tiny problem. Remember, we have so far discussed everything considering a two-dimensional representation of pixels, where we identify a pixel with a row coordinate and a column coordinate. But the digital image file stores these pixels as a single dimensional entity, that is as a single row of pixel data. We need to come up with an idea to map the two-dimensional coordinates of the pixel into a single number that represents the pixel in the file. In the first video, I explained how the BMP file format works, and in that I said the file stores pixels starting from the bottom left corner of the image going to the right, row after row till it reaches the top right pixel. So the pixel at 0, 0 goes to position 0, the one at 1, 0 goes to position 1, and so on, and the pixel at 5, 0 goes to position 5. Next up, the pixel at 0, 1, which is one row above the bottommost row, goes to position 6. Here we notice two things. The position number of the pixel on the file goes up continuously, whereas its x-coordinate increments continuously only till 5, at which point it rewinds and the y-coordinate increments. Therefore, we could say the position of the pixel on the file, P, is equal to the x-coordinate for the first row, that is row 0. But for rows after that, we have to multiply the y-coordinate of the pixel with the pixel width of the canvas and add the x-coordinate to that. This gives a continuous mapping of the two pixel coordinates on the canvas to its position in the file. So in general, this formula holds to map any pixel on the image into its corresponding position in the file. Okay, now we can actually write the program to draw the thread from nail 7 to 25. So let's go ahead and do that. We know the position of the two nails and the total number of nails on the canvas. So let's put them here first. And then let us calculate the radius of the nail's pitch circle, which is half the image width. Remember, we have already acquired the width at the start of the program. Next, we shall calculate the angles subtended by those two nails at the center of the circle and their sines and cosines. These trigonometric functions are available in the C math library, and therefore you need not roll out your own routines. And finally, we shall calculate the slope and the y-intercept of the line using these numbers. Before we continue further, let us do a sanity check whether the program outputs the correct values for M and C at this stage by printing out their values. Let us compile the program, and there appears to be an issue which we shall fix and recompile the program and run it with our image, and yeah, it appears to be running correctly. We have the correct value for M and C as expected. Let us write the code to traverse through each unit of length along the x-axis. Here inside this for loop, the variable I gives the coordinate on the x-axis, and therefore it goes from 0 all the way till image width minus 1. So at each iteration of the loop, we shall determine how many pixels along the y-axis we have to shade using the formula we derived earlier. Remember, at each unit of length along the x-axis, it is possible for the y-bounds to be multiple units of length apart. And because of that, we may have to color multiple pixels vertically. Therefore, the second for loop here runs as many times as there are pixels to shade vertically, and the variable k gives the bounds of the y coordinate of those pixels. Inside the loop, we shall set the color of those pixels black by setting the color value to 0. But there are 4 channels per pixel, 3 colors, red, blue and green, and an alpha channel. We shall set values only to those color channels which are the first 3 and leave the alpha channel untouched. And because there are 4 channels per pixel, any 2 pixels are located 4 bytes apart. Therefore, we have to multiply the pixel coordinate to pixel file location mapping formula by 4 for each pixel to get the correct rendering of the line. Let us compile and run the program on my cat picture, and there we have it. The line looks good. It is indeed the line we were looking for. Now that we have come this far, I would like to draw some more lines from nail 7 to see how that looks. Let's see. I shall draw from nail 7 to every nail that follows it, all the way till nail 49. For that, we just have to put the code we wrote previously into a loop, which loops over the choice of the second nail from an offset of 1 from the first nail till the last nail, and that is pretty much it. So in this example, the second nail would go from 8 all the way till 49. So let's run the program, and we have the segmentation fault. Why did that happen? Oh, it looks like the Y bounds could overshoot or undershoot the bounds of the canvas inside the second loop. So let us put some code to check when that happens, and if it happens at all, we shall cut that loop short. With that, let us compile and run the program again, and it looks like it worked. That's good. But if you take a closer look, you would notice some of the lines missing. Specifically, those lines whose slopes are negative appear to have not been rendered on the canvas. This is one of the drawbacks of the inequality we derived earlier from the slope-intercept equation of the line. We could fix that easily, trust me. But before we do that, let us take a look at another even bigger problem that could derail our entire algorithm. These lines are too dark and appear too jagged, and honestly, they don't look like thin strands of thread at all. So in the next video, we shall take a new approach that could actually make these lines look like real threads or pretty close to it. The code you saw in this video could be found on GitHub, whose link is in the description.